So let's see in chapter 2 what are the important points. Okay. So chapter 2 is molecular and ionic compounds, structure and properties. Basically, different kind of chemical bond we are dealing, and yeah, what are the other thing? Mainly that Lewis structure, polarity, resonance, VSEPR, the structure like that. Okay. Weightage as usual like 79% only acids and base, and chapter 3 how higher weightage, right? Okay, don't want to be intimidated by seeing this one. Just I'm showing everything in one structure, like one picture. Okay, so let's see what are the stuff. So first, like the chemical bond, the most stronger bond like that, like in our according to your syllabus, you can study with a network covalent bond, and then metallic bond is there, and then ionic bond is there, like then covalent bond. Only these four bonds you are dealing, right? Coordinate bond or other stuff you are not dealing. So these are the four different kind of bond you are dealing with. So according to that, network covalent is highest one, and then metallic, then ionic bond, then covalent bond. Okay, right. Main point we need to memorize with the network covalent, only carbon silicons are forming this network covalent bond, like graphite, diamond, silicate. Whenever these things are in your question, you can identify it is a network covalent bond. Okay, only with the graphite, diamond, silicate, like that kind of example. Okay, so those are usually non-conductive except graphite. Graphite is conductive and definitely highest melting point and boiling point. Okay, and then metallic bond, as you know, metal bonds are metallic bond. Then definitely they are conductive in even in solid state, and high melting point, boiling point, but lower than network covalent. Then insoluble in water, and most of the metallic properties is like defined by C of free electron. Any metallic property, suppose you need to explain why it is so behave like that, why it is behave like this. So all of them you can just tell C of free electron, right? So metals, you know, if Fe is a metal, what happened? Usually all the metal loosely bounded electron you can find, right? So always they are like a C of free electron. That's how its behavior. So that's why we are defined every characters of metal. Okay, and alloys are very important. Like the question be like out of the following which one is forming substitution alloy, or which one is interstitial alloy. At that time, see, just imagine substitution means you are substituting one with another, right? At that time it will be same size, but interstitial means they will occupy in the interstitial position. Alloy means mixture of metals, correct? So at that time, or every time, what different sized things will form an interstitial thing, and same sized thing will form a substitutional thing. Okay, so this will be different size, and the other one will be same size. Okay, right. And then ionic bond, the main points are like, metal and non-metals are the stuff. And also they are conductive only in molten or aqueous state, right? Okay. Then high melting point, but lower than metallic bond. And soluble in water. Main thing, lattice enthalpy is the main stuff. Which one having highest lattice enthalpy? So you need to think about like what Coulombic law of attraction, isn't it? Charge over radius ratio. Don't want to make the ratio, but just think about first you can made a comparison, make a comparison with the charge. Higher the charge, higher will be the attraction between the ions, correct? So that you need to spend a more energy in order to break the lattice. That is what we call the lattice enthalpy. Okay, if the charges are same, then you can think about the radius, right? For example, if you are comparing NaCl and the other one is, maybe you can't see here. If you are comparing NaCl lattice enthalpy with MgCl2, okay? So here, this is plus 1, this is negative 1. This is 2 plus, this is negative 1. Which one is strongly bounded? Yes, higher charge will be higher attracted. So MgCl2. But suppose CaCl2 is also be there in the option, what happened? Ca is also 2 plus and minus 1. So at that time you can think about radius. Radius is lower for, as we top to bottom, as we go top to bottom, radius will be increased. So magnesium have lower size. Lower size means higher attraction. So MgCl2 will have a higher lattice enthalpy. So that's the main thing about ionic bond. And then covalent bond. Covalent bond is formed by non-metal. Definitely they are non-conductive. The lowest melting point and boiling point, right? And soluble in water. Okay, so these are the important points need to know with the chemical bond. Okay. Then in this chapter, we need to know with the Lewis diagram, how to draw the Lewis diagram, because everything after this one, like if you want to get the IMF or polarity or the shape, everything, we need the Lewis diagram, right? So how to draw the Lewis diagram. So first step, count the total valence electron. So for example, I can write SO2. First step, count the total valence electron. Sulfur have 6 valence electron, oxygen is also 6. So altogether there is 18 electrons are there, right? Okay, and then draw the skeleton structure. So we are assuming at least one bond exists in between these things. Then only SO2 like that molecule is there, right? So we are assuming at least one bond, so that you are already shown that 4 electron. We need 18 electron totally to show, but already we shown that 4 electrons, right? So the remaining electron is 40. So see this third rule, distribute the remaining electron to the side atom according to the octet rule, right? And then to the central atom. So this oxygen needs 6 more, and this oxygen also needs 6 more, and see we have a total of 14, so the 2 electron is remaining. And then see the last rule, check the octet rule for the central atom. If it's not satisfied, do delocalization, which means sulfur C 2 4 6 only. So definitely you need one, sulfur need one more electron, so this electron is shifted to that one. So this is the Lewis diagram of SO2, right? There is no charge, so no need of bracket. Clear? So see, now sulfur is satisfied, 2 4 6 8, and everything is satisfied. So this is the Lewis diagram. But see, sulfur dioxide, this is not only the Lewis diagram, okay? Some molecule can do more than one Lewis diagram. For example, I can show you the sulfur, like see, so for sulfur dioxide what we got is this one, right? So one is double bond and the other one is single bond with a 6 valence electron, here 2 4 valence electron, and the extra valence electron is on the sulfur. Okay, but sulfur dioxide you can also draw like this. Why? Because sulfur is in the third period, right? So in third period onwards more than octet is possible. So expanded octet, like sulfur can accommodate more than 2 electrons, so 2 4 6 8 10 electron, yeah, no issue. So this is also the Lewis diagram of sulfur dioxide. So which one is stable? At that time you can use the formal charge. Okay, so see, so in structure 1 what is the formal charge for sulfur? Valence electron is 6 and the lone electron not like a pair, so 2 electron, and the number of bond 1 2 3 bonds are there. Okay, so 6 minus 3, so just 1. And oxygen, this oxygen I'm just writing A and this is B. So again 6 electron, valence electron, and the lone electron is 4, and then 2. So the valence electron, sorry, the formal charge is 0, right, for OA. And OB means this is structure 1, this is structure 2. OB means 6 minus 4, not 4, 6 actually. 6 minus again 1. So minus 1 will be there. So this is the formal charge. And what about structure 2? Here also sulfur is 6 valence electron, 2 lone electron, but now there is a 4 bond, so there is only 0 charge. Oxygen OA, same same OA, so this is 0, this is also 0. Okay, so see the distribution of charge. Here it's more zeros are there, right? More zeros means that will be the more stable structure. Okay, concentration of charge should be lower. Okay, distribution have to be maximum, like so total charge always, this one is also 0 and the other one is also 0. Okay, we studied a resonance structure in this chapter. For example, carbonate, so CO3, so in which one is double bond and the others are single bond, 2 minus. Okay, so this is also you can draw like double bond here and here, so it's delocalizing. So 2 minus, again that oxygen, here it is double bond, right? And this is single bond. Okay, so in this way you can represent the resonance structures of CO3 2 minus. So oxygen is like that its double bond is changing. Okay, so here can you tell me what is the bond order? So what was bond order? Do you remember? If it's a single bond, bond order is 1, double bond order is 2, triple bond order is 3. If it's so, in the CO3 2 minus, do you expecting a 2 bond order? Like see, bond order, single bonds or bond order is there. Similarly, double bond order is there, which means two single bond and one double bond. Like that, can we expect? No. Okay, bond order is, there is no two bond order, like bond order 1 and 2 is not there. In resonance structures, bond order will be calculated like this. Okay, that's maybe better. In other case also you can do, but here it's more valid. Okay, because there is not like specific double bond here. Always that double bond is delocalizing. Okay, so you can't say this one is always double bond, this one is single bond, like that. There is no double bond length exist. CO single bond, okay, CO single bond is 90 picometer. CO double bond means more lower, so 80 picometer. Not like that. You can't see any two bond length here. In this case, kind of cases, there is only one bond length, which is 75 picometer, like the average of this thing, right? It's, if it is exactly 1.5 is the bond order. Right. So how do you calculate the bond order? Number of bond divided by distributing atom. So here how many bonds are there? So every structure 1, 2, 3, 4. 4 over 3. Distributing atom is 3. 3 oxygens are there. So 4 over 3. 1.3 is actually the bond order. There is neither one or two bond orders. All the bonds are same. That's the resonance specialty. All the bonds are same. Okay. Right. If it's so, if all the bonds are same, then see, what about this question? Here the two loose diagrams are given and they were telling you need to find the correct statement. Okay. So the first option itself, all bonds are same length. So here I told like it's resonance have same bond length, like that I told, isn't it? So that would you choose A? Here one thing is there. See the resonance structure. The resonance is only between this oxygen and this oxygen, right? These two oxygen, these two bonds are take part in resonance, but they were not what this SO bond is not take part in resonance. That's the problem. So that's why all the bond is not equal. Resonating bonds are equal. So resonating bond means this SO and this SO. I will show. This SO and this SO is resonating. So there will be two identical SO bond and one SO single bond. So why this oxygen is not take parting in resonance? Because see, all this oxygen is already double bonded, right? Like double hydrogen combo is there. Suppose this oxygen is double bond, like sulfur double bonded oxygen is there. Again, it will do with like a triple bond, like not triple bond. See the bond order, like surrounding oxygen, there is a 3 bonds. That is not possible. Usually oxygen will not do that one. Okay. At the same time here, if single bonds are single bond or double bond, no issue. There is no other atoms, right? So this oxygen, there is no issue. It can be single bond or double bond. But this oxygen with a triple bond, if this oxygen is take part in double bond, like resonance, they will make a triple bond, like not triple, they will make a 3 bond, like valence is 3. That is not possible. Okay. So that's why this oxygen is not take part in resonance. So there will be two identical SO length and the other SO length is there. Okay. So which one is smaller? Is this like what the not that one is not take parting in resonance? Is it having a lower bond length or the other one having a bond length? That will again tell the bond order, right? As you know, bond order increases, bond length decreases. So here this oxygen, so I can write this is A and these are resonating, like that I can write. Okay. So what I told, there is two SOR. Okay, resonating oxygen bond length is there, which are same, and the other SO bond length, SOA bond length is there. Okay, so which is the bond order? Here it is clear, bond order is just 1. What about this SO? Here it's resonating, so you can easily apply the formula, like 3 bonds are there, 3 over 2 atom, distributing atom. So 1.5. So higher bond order, yes, more stronger the attraction, so bond length will be very lower. So there is two SO bond length lower, like lower bond length are there, and one larger bond length is there. Okay. You can choose any option like that. See the thing, of the 3 bonds, there are 2 longer one. No. Of the 3 bonds, there is 1 longer and the 2 shorter ones with identical. So B option will be the correct one. Okay. The other main topic in this chapter is, yes, BSCPR theory and the shapes. We aware about that one. See the AX2E0 type. AX2E0 type means lone pair is 0, A with the 2 bond pairs, right? X representing the 2 bond pairs, right? So one is this one is this one. So 2 maximum distance, yes, linear. Linear, and the bond angle is also very important, 180. 180 will be the bond angle. And AX3 E2 means, yes, 3 maximum distance, trigonal planar will be the shape, and the bond angle will be 120. 4 maximum distance like tetrahedral will be the geometry. Maximum distance, why I am telling is just for in order to avoid the maximum like repulsion, right? In order to avoid the repulsion, they are tend to occupy the maximum far away. So the shape will be tetrahedral with the 4 electron. Okay, so 109.5 will be the bond angle, and 5 maximum distance trigonal bipyramidal, and 6 maximum distance like octahedral. These are the basic shape. And then, as you know, if lone pairs are there, there will be 2 geometry. One is electron geometry. See, this is their electronic geometry. AX2E0, this is their electronic shape as well as molecular shape. Both are same. Molecular geometry as well as electron geometries are same. Okay. But if lone pairs are involved, there will be 2 geometry, molecular as well as electron geometries are there. So electron geometry is just count the total electron. For example, see, suppose AX2E is the stuff. AX2E means 2 bond pairs are there and 1 lone pair is there. So total electron cloud is 3. So 3 maximum distance means trigonal planar. Okay, electron geometry will be the same, trigonal planar, but molecular geometry will be called bent. Okay, 3, or you can just imagine 3 minus 1, trigonal planar minus 1. Like what I mean by trigonal planar minus 1, like altogether 3 electron cloud is there, but 1 is lone pair. At that time you can call the shape like bent, and the bond angle is same like 120, similar to 120, but it's not exactly 120. For each lone pair you can deduce 2 points. Okay, so this is with the 1 lone pair, so we can write minus 2 like 118. Okay, then tetrahedral minus 1. So what I mean by tetrahedral minus 1, AX3E. Okay, altogether 4, but 1 is lone pair. That is called a trigonal pyramidal. Trigonal pyramidal. And tetrahedral minus 2, it's again bent. Tetrahedral minus 2 means it's again bent, but bond angle is different because this one is originated from the tetrahedral geometry. So the bond angle, like, you can reduce 2 digit because 4 digit, right? Because 2 lone pairs are there. So it's around like 105. Okay, that's it. And the trigonal bipyramidal, like 5 minus 1 is there, altogether 5, but minus 1, which means AX4E is called a seesaw. This one is called a seesaw. And trigonal bipyramidal minus 2 is called a T shape, which means the thing is AX3E2. Then trigonal bipyramidal uh, minus 3, right? So AX2E3 is called a linear. And the octahedral minus 1 is square pyramidal, because square bipyramidal is octahedral, right? So one electron is lost, like lone pair means square pyramidal, and the other one is square planar. Okay, so these are the basic shapes. Okay, after that you need to know with the hybridization. Hybridization is also very easy. For just imagine s orbital, there is only one orbital. It's just like an odd number. P, how many orbitals are there? It's just like odd number. S have one orbital. P is divided into 3 orbital. This is 1, this is 3. So obviously D is divided into 5 orbitals. Okay, 1, 2, 3, 4, 5. 3, 4, 5. Okay, one more is. Okay, got it? So this kind of orbitals are there. Then you just count the total electron cloud. Okay, only you have to count the total electron cloud. So for example, AX3. So total electron cloud, like E0 means total electron cloud is 3, right? So the 3 means the hybridization will be, you need to get the 3 hybrid orbital. So one is you can take it from S, and the other mixing, like this is actually mixing of orbital. We need 3 mixing, 3 orbital have to mix. So what are the mixing? One is from S, and you need another 2 more. So sp2 hybridization. Okay. Then suppose it is AX2E. See, AX2E means again the total electron cloud is 3. Even it is lone pair, the total electron cloud is 3. So what may be the hybridization? Yes, again first one 3 you need to make 3 hybrid orbitals. So one is from S, S can only provide 1, P can provide up to 3. So again sp2 hybridization. Okay, suppose your thing is AX2 like AX3E2. So AX3E2 means totally 5 electron cloud is there. Yes, isn't it? So 5 hybrid orbital you need to provide. So 5 hybrid orbital means S can provide only 1 and P can provide 3, and yeah, sp3 means only 1. 4 is there. So one more is needed. So that is taking from the D. So sp3D will be the hybridization. 3 plus 1 plus 1, 5. Okay, that is the hybridization. Right. Then a simple thing, sigma and pi bond. See, how do you count the sigma and pi bond? Suppose this is your compound. All these things are hydrogen. So which one is sigma? Some students will mistakenly do like this is pi and this is sigma, this is sigma, this is sigma, this is sigma. Not actually. So how do you count? Only additional bond is pi. Only additional bond is pi, which means C double bond C is there, and here this one is there. So one hydrogen, 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 right? So what's the problem? This is sigma, every first bond is sigma. So C double bond C is actually sigma, and the additional bond, see there is a double bond. So the additional bond only you are considering like a pi bond. So there is totally 1, 2, 3, 4, 5 sigma and 1 pi bond will be there. That is the stuff. Okay. That's all about the chapter 2 things.